Is he remote? Yeah, okay. So, Matthias, the first is remote.
Paul Schmidt is remote, yeah.
That's the same we had before. Yeah, that's right.
Paul, can you hear me?
Yes, I can hear you.
Paul, do you want slide control? Like, ask me for slide control.
Yeah, I have the request up.
Okay, so welcome back everybody to the Applied Networking Research Workshop. I hope you had a pleasant and enjoyable lunch and you are now fresh and not tired, because we have a really exciting session about network measurements, 7 long papers and 1 short paper. And the first presentation is given by Paul Schmidt about PCAP-ML, making network traffic data sets reproducible. Please go ahead.
Okay, thank you. So again, I'm Paul Schmidt. I'm at Cal Poly, and this is work stemming back many years from when I was at Princeton with Jordan and Nick, and who Nick is now at UChicago. And yeah, we're looking at reproducibility. So likely many of you in this room have worked on machine learning and networking traffic, and you have probably run into all sorts of problems. And this paper, unfortunately, we didn't think needed to exist, but we just keep running into the same problems, and we decided to put it together. So any network traffic machine learning problem depends on labeled traces. So we use this for traffic classification or denial of service detection, all sorts of things. But unfortunately, dataset pipelines are very often underspecified. And so you've probably had this experience. You see somebody's new paper that has really promising results, and you want to try it out. And maybe they were kind enough to actually release a data set. And so you download all of this and you try to rebuild essentially their pipeline, and you don't see the same results. And the issue is that the same raw traffic, even when people are kind enough to share their data sets, can end up becoming very different data sets. And that's what we're looking to attack here. And so from our point of view, one of the major weak points we see are that labels tend to live outside of traces. So if people release their data sets, they've got a set of PCAPs, and then alongside of those PCAPs are some kind of labeling or metadata data sets, so text files or what have you. And if I see this interesting paper and I want to reconstruct it, well, I need to join these two pieces of data using sometimes timestamps or time windows, tuples, file names, feature files, etc. And the challenge here is that really small choices become quite consequential. And so what is your definition of a flow versus my definition of a flow? Some people combine unidirectional flows and make bidirectional flows in their data sets. Some choose different timeouts. We've got different class mappings. And of course, there's training and testing splits that are not always available for us to see. And so the end result is that papers can compare accuracy numbers against prior work or prior techniques, and they will be essentially evaluating fundamentally different tasks or comparing apples to oranges. And this sort of annoyed us to the point that we decided to try to write this paper. And so in the paper, we go through a handful of these examples of very popular sort of canonical data sets that a lot of people rely on. And one of those is VPN, non-VPN. So this data set's released as a set of PCAPs with the application metadata encoded as file names. So things like email.pcap or browser.pcap. And that original data set had 14 classes. So it's 7 applications with and without VPN. But the issue here is that the data set itself, of course, doesn't enforce mapping for later use. And so papers that came along after the fact derive completely incompatible class sets from that exact same raw traffic. And so in the paper, we do a small survey, and we see class counts ranging from 2 to 31. And this is not unique to a single data set, of course. So I mentioned VPN, non-VPN, and the root cause there is that these file names don't map to a single class set. CIC-IDS, lots of people use that data set, but subsequent work found that something like 20% of the labels or the flows are simply labeled wrong. And work after that fact has not actually corrected it. And so you end up with a situation where you've got multiple papers working on the same data set, but they've got completely different ideas of what the data set actually contains. UNSW is a slightly different one that a lot of people have chosen to model that as a binary classifier or build binary models versus others have done multi-class using that same data set. And that's going to change your accuracy numbers by double-digit percentage every time. And then, of course, there's DARPA, which has been around forever, and it's known to essentially the metadata files have all kinds of errors in them, and trying to reconstruct these data sets is virtually impossible. And so that motivated PCAP-ML, which from an engineering point of view is very, very straightforward. There's not a lot of deep novelty here, but we wanted to try to lower the barrier here, and we wanted to build a framework for creating self-contained labeled data sets. And the basic idea is we're storing arbitrary labels directly in the PCAP files themselves. And we built it to support 2 different paths. So the first is with live capture using eBPF. And then we also have offline conversion. So if you've built a pipeline and you want to release it as an artifact, you can do so. And we really just want to stop spending so much time on dataset specific reconstruction. We want to take these mysteries out of people's hands as much as we can. And so ultimately, we abuse the PCAP-NG comment field, which is available. It's unstructured text, essentially. And so the nice thing about using PCAP-NG is existing tools get to still read the trace. So this is a snapshot, a screenshot of Wireshark with a PCAP-ML trace. And you can see the comment field has a sample ID, a process ID, a direction, and a destination. So we just throw these keys in and the data we can grab for any trace, and we can just put it directly into the PCAP for later use. By default, we tag every packet with a flow level of a 5-tuple sample ID. And the idea there is that at the very least, we should be able to have trained test splits reporting their sample IDs that were used rather than forcing people to reconstruct using file names in later analysis. So like I said, there's these 2 paths to creating this trace. The first is live capture. So we chose to use eBPF. The reason being is, well, it's relatively fast, and you can get socket to process mappings directly in the kernel. And so at collection time, we're able to say, oh, this packet can be attributed to Chrome, or this packet can be attributed to SSH or what have you. We also built a module to parse destination labels using DNS or SNI. And the reason we do that is since we built it as eBPF, we imagine this isn't just going to be running on end hosts. It can be run on middle boxes. So I'll talk about a small analysis we did. We ran that on OpenWRT, and we were capturing both at an end host and OpenWRT. That gateway is obviously not going to have process context, but it still has the DNS and SNI destination stuff. And then we also built the offline conversion. So of course, we're not crafting ground truth off nothing. It has to have been captured in the first place, but you can record your construction for later use. And so, for example, you could choose how you're going to represent VPN, non-VPN, and then publish that as an artifact with your paper. And so we did a very small evaluation on this. We did controlled collection using Linux. We ran 5 sequential generators. So first was Chrome browsing and Firefox browsing. Those are basically just top 100 sites that we're going to. We then did Chrome streaming. So we went to YouTube, to a number of videos. And then we did SSH and rsync to show essentially a failure mode. And we were capturing both, like I said, on the Linux desktop and on an OpenWRT box that was essentially unmodified, but running our eBPF module. And so the evaluation is pretty simple. What we're trying to illustrate is what we can piece apart using these different vantage points and the amounts of the different pieces of information we have at each location. So if you have the process label, you can't really differentiate between Chrome browsing and Chrome streaming. But if you have the destination, you can. It's kind of obvious. You see YouTube destination domains versus all of the other domains. Conversely, if you're doing Chrome browsing versus Firefox browsing, the destination labels are not going to be helpful. You're going to those same sites, but the process label now comes into play, and you can peel those apart very quickly. And then the sort of null result or the negative result we had was rsync versus SSH. Ultimately, rsync uses SSH under the hood, and so the tool we're using to attribute socket to process mapping is just going to show SSH for everyone. So that is a failing. So obviously this is not a perfect solution, but we think it's useful. And so one thing we were interested in is a lot of data sets will have these time windows or timestamp based labels. And we were wondering how often that can be a problem. And so we were looking at this, and it turns out during that Firefox trace, something like 5% of the packets were not actually necessarily generated by our doing. Some of those are the DNS Firefox threads, and others were something else. Some of them were from our WebDriver, some of them were just random other traffic. And so when you do this, you can start to attribute things to the appropriate process, and we hope that this can sort of clean things up and make it easier to train models that aren't necessarily looking at noise. And so just to wrap up this very simple approach, we don't think the packet traces are complete benchmarks if you're forcing people to reconstruct using labels after the fact. So very simply, we store those labels, and you can store arbitrary text inside of directly in PCAPs at capture time or offline. We don't fix everything. We're not standardizing your task definition. We can't infer things that weren't captured or were encrypted. We've built a handful of labelers for common cases, but the framework's extensible, it's open source and available. And the whole idea is we want to save everyone time, and we want to save our own time when we're dealing with these sorts of data sets and problems. So like I said, it's available, it's Go. Of course, it would make sense if we moved away from eBPF to something like PCAP, if you want to run it on Windows or Mac. And we also built a pip installable module. So you just use that, you can pull in a PCAP ML, and it can pull directly into a Pandas data frame and have all the columns labeled for you. So with that, I'd be happy to take any questions.
Thank you very much, Paul. So any questions? Please, reminder, log into the data tracker anyway, that we can record your participation. So Danish has a question. Go ahead.
Behind you.
Oh, sorry.
Hi, thanks for the nice talk. I want to know what is the overhead of labeling while we are live capturing the packets?
We weren't able to sort of find a limit where it fell on its face, although it was capturing on a moderately powered desktop and on OpenWRT, and it was a moderately powered OpenWRT router. So we didn't see the limit, but certainly it's not going to be free. And you're adding that overhead of storing these labels in your PCAP. You're definitely inflating the PCAP size.
Thanks.
Further questions? Maybe I have one in between. So you're actually using the comment field of the PCAP-ng file syntax, right? I'm just wondering whether this could also, if you only add the 5-tuple or metadata, I'm wondering whether it would help to ease and scale the processing if you would add additional data about the whole packet structure, something like, oh, this is a TLS packet, oh, this is a quick packet. Question is whether you check this in the processing chain of TCP dump and all of these filters, whether the comment field is processed before all of the details of the packet itself.
Yeah, that could make sense. So we didn't do that at first because we figured these tools will be able to parse it. But certainly, if you wanted to sort of offload some of that work, you could just put that directly in the comment field and make it lighter weight later. Yeah.
Could make the processing more scalable. Yeah.
Sure.
Okay.
Yeah, that's a great idea.
Cool. Any further questions? 1, 2, 3. No, really cool tool. Thanks again. And yeah.
Thank you.
So our next speaker is Benedict, who should hurry up. Quick. He is a PhD student with Jörg at TU Munich, and he will talk about NixNet reproducible virtual network experiments. So supporting measurements is the theme here. Thanks.
Thank you for your nice introduction. So this talk is about NixNet, reproducible virtual network experiments. This is joint work with Marcin, Paulo, and Jörg.
Yes.
Yeah.
Okay. Does it?
Should work, yeah. I gave you control.
This one doesn't.
Yeah, control. Let me stop.
I can also. Can you change the slides?
Yeah, just call it out to me. I'll change it.
Oh.
Yeah, I'll change it.
Okay. Oh, good.
Now it works?
No, I did it. Yeah.
Okay. I just say next slide. Okay.
Yeah.
So network experiments are hard to reproduce in practice and harder than it should be. Next slide. Main problems are that dependencies of experiments are underspecified, resources are no longer available, package managers don't have the right version that you require to run it. The build environment that you are using is not the same that the original authors had. Same for running or for building, although you might not know the compile flags that the authors used. For running it, similar thing, different JIT compilers, different interpreters. The host machine is different OS, different configuration, and leftover applications from previous experiments or long-running systems. Next slide. We want to be able to run today's network experiments tomorrow and even 10 years from now. So we want to preserve them. Next slide. Why is this important? It's important across all the areas, academia, industry, teaching. We want to build on prior work and not reinvent the wheel over and over again. We want to test interoperability between different programs written in different languages, even comparing old to new software in some test scenarios, analyzing bugs, understanding their behavior in general. And also for teaching, it's important to have something you can share with students and not that the students have to set up or spend a week to set up some test bed by themselves for a week. Yeah, for a week. Oh, and next slide. And what we are focusing on here is emulated test beds. So in contrast to simulated test beds, so simulation is more flexible, but also more model-based, right? It's not testing the real software, but often we are interested in running real browsers, real server applications in an emulated test bed. On the other side, you can get more realistic results if you have hardware test beds, but they are expensive, time-consuming to set up. So emulation is a good middle ground, I would say, and that's what we're focusing on in this paper and also talk. Next slide. The state of the art, there are many great tools already. You might be familiar with Mininet, Container Lab, ContainerNet, or have handwritten your test setup with some bash scripting and TCNetDM. They are great tools, but they are facing some challenges. On the one side, you have a lot of side effects from your system, either from your host system or also experiments that leak to your experiment, because dot files, configuration files, some caches that are placed somewhere, so no isolation. The dependencies are not managed, so your experiment is using programs that are on your host you might not be aware of, so some libraries, and you don't specify them because you don't know that your experiments actually depend on them. Handwriting is error prone, and if you use Docker solution, then you get a lot of isolation benefits, but they are more heavyweight. You have to use the images, and Docker images are not reproducible from source per se, and they are quite heavy in also startup. Next slide. That's why we built NixNet. This is what we created and what the talk and paper is about, which manages the full dependency graph of the whole experiment. All the software is managed. There is no manual setup required. The build is hermetic, so isolated. The build is the same thing as your previous author did, and also the execution is isolated from the host system. So no leakage there. It runs on any Linux machine, on a single machine, so similar to a mininet. You can run it as simply as just executing a single command. No root privilege is required, which other tools often or mostly require, and no manual setup. So no leftover state that can leak into your next experiments or fills up your disk, just the results you care about. Slide. How does it work? Sounds good, too good to be true. Next slide. Let's start with dependency management. Next slide. Next. Dependency is managed with many tools that you today use, like, that's the state of the art. You version your software or code with Git, but it's nice because it's tiny, it's only storing the diffs of code, but there's no instructions how to build this thing, and there is no instructions or no dependencies on which Git repository is linked to others. You can hack it, but it's not built for that. Docker, on the other hand, is bundling all the stuff together, so you can give it to someone, but giving it to someone is not the same as having the other, or can recreate the same image, because it's often relying on binaries that are fetched from some other dependency managers. And yeah, like I said, no tracking of the sources. Oh, what's going on? Okay. And Docker images are quite large. If you want to preserve them for years, you have to store them. And they are in some registries, but they will be dropped after some time because either you have to pay or have a lot of disks around. On the other hand, there are those known package managers like APT, mostly a really popular one. But this is a binary packet manager. So also you have binary packets that you fetch, which are semantically versioned. So there's a version number on it. But this doesn't actually mean, or you don't know how the one who compiled this thing, or the packet manager, which compile flags are used, right? So if you have different packet managers, the version doesn't really mean anything, that you get the same binary out of it. And also, if there are bug fixes, if there is version changes, the old sources or old binaries are dropped. And in network experiments, we actually want to reproduce or run experiments with the specific bug, because a year from now the bug is fixed, but I don't care. I want to have the bug in my experiment, right? Next slide. So wouldn't it be nice to have something like a Merkle tree, like like Bitcoin or Git works, that you have a dependency graph of a hash that identifies your parts of the system, and with a cryptographic hash, so your node is depending all the child node hashes, and if any of the childs change, your node changes, or your node hash changes. And that's exactly what we want to have for experiments, a unique identifier with which changes when something dependency changes and stays the same. Next slide. And that's exactly what we are using. So this is Nix. So you might have heard of Nix OS. It's the exact thing it's built upon. So Nix handles all the dependencies of software that is used at runtime. So it's the runtime closure. So all the Merkle tree or Merkle graph of all the runtime dependencies, but also all the dependencies that are used during build time. So you have also a build time graph with all the compiler, source code, build flags, everything hashed in a nice Merkle tree. And yes, that's what we use Nix for. Next slide. And with NixNet, I mean, this slide is a bit complicated, but it shows that NixNet actually handles all of, or on the top you see the experiment, this is the hash of the experiment, and all the dependencies. You can, whatever you have in your experiment, configuration, certificates, all the binaries, libraries, eBPF code, packet traces that you want to replay in your experiment, like think of anything that is a file, and this can be tracked with Nix. Next slide. So one Nix expressions or Nix expressions are today used to build packets, but also operating systems, and now with NixNet also network experiments. Next slide. Next slide.
Yeah.
Okay.
Yeah, you have it.
Okay. This is just an example how it will look. So this is just a description with, you describe your nodes in your experiments, you describe your links, you describe the characteristics of the links. And yeah, if you, it is JSON-like. Yeah. Next slide. I have to hurry up, I think. And what NixNet is actually, it's just a really fancy bash script generator. But for a purpose, because I want to have low abstraction. So most of network engineers, we are familiar with how command line bash and or how you configure your firewall and NAT and stuff. So to be transparent, I want to have something readable or not some Python syntax that's on a higher abstraction level. So that's on purpose. Next slide. Now to running the experiments, I have to, okay, I could talk for 2 hours, but I have to squeeze it in 10 minutes. So we have built it, and also running is also isolated. Next slide. We have a next slide. We have a multi-layer isolation process. So we isolate the experiment completely from the host system using the same technologies that Docker use. So this is Linux namespaces. We mostly use all the namespaces to isolate the experiment from the system, but also the nodes inside. You have hundreds of nodes in your experiment. They are also isolated from each other because you don't want to have leakage between them. Next slide. This is what it looks. Just run Nix run, and you get setting up this whole system, building all the dependencies that you don't have built, running it, and in the end you just get an output folder with all the artifacts you want to preserve. Other things is all cleaned up. Next slide. We evaluated this, not evaluated in a sense of we tested what the network performance is, but we tested NixNet in terms of how fast is the setup, because what we think is we want to have a fresh topology set up for every run of the experiment. So if you test because you do repetitions or you sweep across some large parameter sets, but you want to start with a fresh topology for every run. And that's why I think setting up and clearing it down and using less memory is quite important. Next slide. So you can see this, the blue line is the Docker one. This is runtime, it's the startup and clear up phase. And we can, for 100 runs, 8 nodes, we can save 3.5 minutes just for setup and clear up, node running experiments, actually. Next slide. And it's similar for memory, peak memory. I mean, Docker containers, setting up the containers takes a lot of RAM, and we can do much better with NixNet, saving 428 nodes, 90 megabytes RAM. There are a lot of limitations, I think, over time already. Yeah, I can focus, or for example, macOS support is something we want to look at. I mean, we rely on network namespaces. That's why we are targeted to Linux already only, but we can use virtual machines, but because Nix runs on macOS already, so this would be some logical next step. But a lot of things, there are GitHub issues for all of those. Conclusion, there is, I mean, NixNet is pinning the full source dependency graph of the experiment. It's lightweight, using Linux namespaces. It's hermetic builds and hermetic runs, so no leakage between stuff. Low abstractions, like I said, it's bash in the end. And so NixNet experiments, and so when you define your network experiments with NixNet, it's easy to share, preserve, and build upon. Thank you.
Thank you very much, Benedict.
Maybe get to the next slide, just the next slide.
We are out of time, so.
No, just because there's a link on it. Just because if you are interested.
So I really have a philosophical question. Yuval
Yes.
Shavit from Tel Aviv University. You know, no man have ever stepped in the same river twice. If your experiment is so sensitive to all these parameters, what is the meaning of the result?
Yeah, I mean, it's yeah, it's good, nice to see you. I'm not sure if I can answer that, but yeah, it's not deterministic, right? It's not simulation, so yeah, maybe we have to reproduce on purpose stuff, so rebuild stuff on purpose, but maybe if you want to have exact reproducibility or just build upon someone's work, it's probably better to have the thing at hand. But yeah, not sure.
Otherwise, you can continue the philosophical discussions during the break. There's more time.
Hello, thank you very much for your work, first of all. I would be interested in what does your tool offer beyond the pure dependency management, also especially towards network impairment simulation, because that's what I'm interested in.
Yeah. So for network impairments, I mean, we currently support, I mean, technically, I haven't mentioned that, but technically you can also add your own hook points. So you can just call any Linux tooling. So NixNet relies currently on TCNetDM, so what Linux provides out of the box already. So we have also syntax for that to build it, but you can also write the bash line as you would in your terminal. But if you have your own emulator that you want to use, if you want to integrate NS3 or some stuff in this, you can do that. But currently we don't have syntax for that, but feel free to open the issue or create pull requests. So I'm happy to support more emulation tools.
Thanks. Anthony, go ahead.
Thanks. I'm in the same boat, so I'm already running it. You don't have to sell it to me. So but I'll give you one more good selling point is running different versions of the OS. Like if you want to have one side of the host with an old version and one side with the older new version, Nix is one of the best tools out there. So next, the real question. So are you using the Nix network topology builder or are you using your own topology builder to create the networking topology you need?
What do you mean with Nix topology builder?
So I'm assuming your tests have more than one Docker, or do you have more than one Docker?
Yeah, it's not Docker, but yeah, you have multiple network namespaces or multiple namespaces.
So are you connecting them all using Nix topology builder, or did you build your own topology builder for that?
So we built a description, like a schema that generates the bash code that creates virtual network cables, virtual network Ethernet cables between your network namespaces, basically. So
because Nix upstream has a thing, but that is very primitive. I couldn't build any complicated.
No, I think then so NixOS doesn't. I mean, NixOS can configure your whole network, but
no,
I think they don't have syntax.
Nix testing, not Nix OS. Nix has a testing, and the testing is very hard to build the topology.
Okay. I have not looked at the testing framework how NixOS is doing it. Okay, but that's a nice hint. Thank you.
Thanks again. Thanks again to the speaker because we have to rush a little bit.
Thank you.
So our next speaker is Petya. She will explain the routing about incidents, triage.
I'll run the slides for you.
Measurements. And she is.
They couldn't fix it.
Yeah. Sorry for this.
We can try again if you want. I can try with the thing, and then if it doesn't work, let's do it. Oh, hold on to it. Just give me a sec. Try it now.
Right now?
No.
Then you have a human clicker. Just
So if you have your laptop, I can give you slide control and you can present from your laptop. It's easier for you.
Can I stay next to you?
Yeah.
yeah, go ahead.
Thank you.
I don't know if the camera is going to track you.
Okay, thank you.
Okay, let me take back control from the clicker. Okay, now it's yours. Just right arrow, left arrow. Yeah.
Okay. So, hi everyone. My name is Petya Vasileva, and today I will talk about the explainable routing-aware incident triage from active measurements that we implemented for the needs of the WLCG network. So,
Just give me a sec.
space? No?
Right arrow. Yeah.
Okay. So LHC stands for Large Hadron Collider. This is the biggest machine ever built. Its purpose is to produce subatomic particles and smash them in the collider. The reason for doing that is to reproduce the conditions right after the Big Bang. So particle physicists collect this data and analyze it, record it, replicate it, and so on through the worldwide LHC computing grid. So the home for this collider is CERN in Geneva, Switzerland. And about 20% of the computing and storage capacity is really at CERN. The rest is distributed across the world. Thus, data needs to flow between sites continuously. The last reports I read was saying that scientists transfer up to 10 petabytes daily of data. So a reliable network and high-performing network is crucial for the scientific community. Thus, we deployed Personar toolkits. I don't have time to explain what Personar does here, but what we do is we actively measure the network state, and we record. Thank you. Okay, nice. And we store the recorded data in a central place in Elasticsearch database at University of Chicago. We test different aspects of the network, such as latency, throughput, and the network path through standard trace routes. And we face many challenges. The motivation for this work is that we wanted to use all available data and correlate somehow the network path with other performance metrics. So some of the challenges we face are, for example, the noisy trace routes, the incomplete tests. Also, we have this challenge that the way we build the meshes is that the different tests run at different cadences. For example, the latencies are once every minute, the trace routes once every 10 minutes, while the throughput is much heavier test, so it's once every 6 up to 24 hours. You can imagine how hard it is to align those measurements and correlate them with each other. So whenever we have a complaint that there is a slow data transfer, we would like to know, first thing we would like to know is whether the path was usual or somehow anomalous in order to see where the problem started and what is the location of it. So we came up with this idea of creating this framework, routing-aware incident triage framework. It could be split in 2 lanes. The first one is processing only the trace routes. Essentially, we built a statistical model that can tell us whether a path is anomalous or normal. And the second lane is dealing with the performance metrics, the one-way delay, packet loss, and throughput. This is much simpler because we just use thresholds derived from experience and from past data. Finally, we align those anomalous data sets in time and produce an outcome triage where each category is not only descriptive, but gives us a priority for the people investigating network issues. This is a plot to show you that we validated our framework on 3 historical cases. One is the Singapore hardware failure. Then we have one recurring, much subtler case in Spain, and a planned giant migration of a single router. All of these have different signatures that we can see in our data. And what I wanted to show you here, if we take the Singapore as an example, we started from about 4,000 pairs, monitored pairs, and through different quality gates and triage labels, we managed to focus on only about 120 monitored pairs that we need to pay attention to that were affected by this incident. So how do we represent the paths? Naturally, we build a graph where each node on the graph is either an AS number or a /64 prefix. The edges could be a membership or, and at the same time, we assign weights to them that are representing the real usage of those links. And also we bias the walks that are sampling. We create a set of 300 weighted walks, and they are biased by source AS because we want to keep our graph representation as much as possible close to reality. At the end of this step, what we essentially have is a node embedding. For each of the nodes, we have a vector of 32 dimensions. And the intuition behind this is that nodes that go together very often, they will cluster together, while the new nodes that are unusual will be measurably further from the cluster. Okay. Then we want to know whether a single path is anomalous or not. So what we do is we take all these embeddings for each of the nodes, and for each path, we average the node embeddings that are seen on the path. In addition to that, we built the structural features, which are three features that represent the IP repetition ratio. So whether the path has a lot of loops or not, TTL gap increase ratio, and path length, which is essentially whether the path became much shorter or longer than expected. In the end, we combined the two embedding and structural values into a single composite score. We don't have the time for that, so I jump into the examples. So this is an example from our live application from the Singapore hardware problem. Those 4 plots represent each of the components. This one is about the composite score. So you can see that initially the score was about 0.3. And suddenly when the issue started, it jumped to the maximum of 1. Then the second plot is the one-way delay. And this is the interesting part, because if we see here the normal for this pair, which is Southwest Tier 2 to Taiwan, was about 220 milliseconds. And suddenly it became much lower, about 80 milliseconds. But when we look at the packet loss, we see a significant increase, and the throughput is close to 0. If we look at two examples of comparing paths from the baseline data set and the anomalous data set. We see why this happened. And initially, the baseline path was using the ESNet, I believe. So this is the expected behavior. It should go through the research identification network. And then in the anomalous path, we see commercial transit through other AS numbers. So a detector that was based entirely on delay would consider this as improvement. But since we use all available measurements, we can say that there was a problem and flag this pair. Finally, this is a live capture. In May, we saw this problem in our application first. It was a submarine cable fault between UK and Netherlands. This is a heat map from our application, and the columns represent the destinations, the rows are the sources, and the colors are the different triage categories. So we can see that the Netherlands column and the UK row highlighted in this plot, and the knock ticket confirming the incident came hours later. Okay, conclusions. So using this method and this workflow, we can not only say if something was wrong, but we can actually pinpoint what changed where and how urgent it is to investigate. I should say here that we do not use any other data source except for the personal measurements, no BGP feeds, no additional probing, only the tests we run with Personar. And this is the URL to our app, which is still development version, so it may be a little bit slow, but you can check it out. Yeah, so this work was supported by the National Science Foundation through the OSG Sun Project and IRIS HEP. And I think, yes, thank you.
Thank you very much. So, go ahead. First question.
Hi, nice talk. Anand here from Netflix. You probably have a lot more latency data than trace routes, right? So was there a granularity level that you thought worked better to be able to correlate those two data sets?
I cannot hear you very well.
You probably have more latency data than trace routes.
Yes.
Yeah, so was there a granularity of trace routes that you think work better to connect those two? Because you want to stitch them together, right? Like what frequency were you collecting the trace routes at?
So the trace routes are once every 10 minutes.
Once every 10 minutes?
Yes.
Was that enough to capture any short duration events?
I would say not enough, but this is what is allowed because it takes a lot of space, all this data. We receive about 4 million tests, and this is even half of what we used to get. We should have even more data than that.
Okay.
So I tried to convince my colleagues to increase the rate, but this is as much as I could get. And because this is once every 10 minutes, I realized that I shouldn't be focusing on short-lived problems and focus only on the big problems, like that they last longer.
Sounds good. One quick follow-up. You are making your nodes at AS level and then associating the prefixes. Were you also interested in looking at link level because you get the hops, right? So are you doing any link level analysis?
I couldn't hear you.
When you get the trace routes, are you doing any link level analysis in them, like per hop, or are you collapsing it at an AS level? So if you had 5 hops within an AS, are you putting it as a one node, or are you doing any like basically 5 links within that AS?
So we use the information about the ASSs and also we use the IP addresses, but I course them to /64. And we can talk later because I have a lot to talk about.
That's good. Thank you.
Yes.
Good. Thanks. Further question? Okay, go ahead.
Hello.
Yes.
I'm Sam from University of Twente. I have a question regarding your active measurement tool. So there are already publicly available tools like RIPE Atlas, Keija provides those probes. Why, instead of using that, is there any specific reason of using your own probe?
I cannot really answer this question because these decisions were taken way before I came to work with my colleagues. But I know that the project is built with some of the participants were in my group, and it was a decision on the level of the community. I can check this for you.
Okay, then thanks again, Petya.
Just a quick note in between, ACM just informed that the papers are online now. We are about to put them also on the website with the links, but they're in the ACM digital library.
But maybe you can post a link in the chat of MeetEcho to the ACM digital library, because they are open access anyway. So our next presenter is Anthony. He's an almost first-year PhD student with Olivier at UC Louvain, and he will talk about a somehow old but still a very important topic that becomes even more important considering the current traffic. It's about interdomain multicast routing for modern routers. Please go ahead.
So hello everyone, I'm Anthony, and today I'll present to you our paper. And I will present to you our paper about intradomain multicast routing for modern routers. So before starting, let us review a bit how multicast works and basically how the PIM routing protocol works. So basically, multicast is a point-to-multipoint communication scheme where one source sends the same data to a set of receivers. Basically, a client will notify that they want to receive some multicast data from the source by sending an IGMP or MLD join to the, towards the source, and it basically indicates that you want to receive some data from a source S, which is identified by a specific group G. Upon receiving this join, the gateway will forward the join up to the source by using the shortest path. So basically, here R4 sends the join to R2, which forwards it to R1, and basically the multicast branch is created. Then if we add a second client, because we are in multicast, we want to have multiple receivers, we can do the same for client 2, which once again sends an SGMP or MLD join, which basically depend on the IP version, which will be forwarded by R5 on the shortest path to the server, which is via R3, then via R, which itself forwarded, okay, doesn't want to, okay, which forwards it to R1, and then we have the multicast tree, which is created and is highlighted on the slide in green. So every packet, multicast packet sent by the server will follow the different branches and arrive at the different clients. So to create this multicast tree in the data plane, we need to have some state that are stored on the routers, which is derived from the joins. And basically, as R1 received a join from R2 and R3, it knows that for a specific tuple, SG tuple, it should replicate the packets and send them to both R2 and R3. So one of the problems with multicast is that you need to have states, and every SG state, which correspond to a multicast flow, require an entry in the multicast fib. If we look at the hardware amphib capacities of different routers, we can see that they span multiple orders of magnitude, ranging from 1,000 entries for low-end devices up to several hundreds of entries for high-end routers like Cisco 8000. So what could happen in practice is that you have state exhaustion. And we highlight this in our revised example. So let's consider that we now have limited number of multicast fib entries on routers, and we add this to the example by showing the maximum number of mfib entries and also the remaining number of mfib entries for each router. Basically, what PIM does is that if we rerun the example, we will send once again a join, and upon receiving the join, we install the entry in the mfib, so we consume one entry on F4. Then PIM forwards it regardless of the amphib entries to R2 because it doesn't consider these entries. And R2 sees that it has no remaining amphib entries. So what it does currently is simply it ignores the multicast join. It does not install an additional entry. And this is quite annoying for the client because it joined the multicast group, but in the end, it does not receive any multicast data ever. And from the client point of view, it is even more annoying because it doesn't really know the reason for this lack of reception. It could be due to exhausted state, it could be due to multicast configuration issues at the routers, or it could even be a packet loss. And depending on the actual reason for this for the lack of reception, the actual reaction that the client should take is not the same. So this is quite annoying. So in our paper, what we propose is to expose these multicast capacities in the control plane and then use this information to route the join around routers that have no remaining entries. So for the first part, we want to expose the entries, and to do this, we simply reuse the existing link state protocols. So basically, we use OSPF or ISS and add an additional TLV that includes the multicast FIB capacity and the remaining number of entries, and then we rely on the link state protocols to flood this information in the whole network, and eventually, thanks to flooding, every router has a global view of the remaining amphib entries for all other routers in the network. In practice, we don't really want to flood this information every time an entry is installed. So in the paper, we propose a threshold-based approach with hysteresis, which basically means that we send the new LSP with this capacity information only when the number of entries are significantly enough changed. So this is quite similar to the traffic engineering extensions that are already existing for SPF and ISS. So once we have this information, we need to find a path because we want to avoid these exhausted routers. And to achieve this, we propose two path computation approaches, which are basically prune shortest path, which simply remove the routers with exhausted entries from the graph and then run a simple shortest path on the resulting graph. Or we can also use the shortest widest path, which basically try to find a path with maximum number of remaining entries along the path. So in both cases, on the example, we end up with the green path where we want to use the path via R5 and R3 and then R1, which has plenty remaining entries to install the multicast state. In practice, when we send a join, we also encode the full path in the PIM join, simply to avoid deflections that could result from delayed LSPs or diverging LSDBs. So we put the full path in the PIM join, and then the PIM join is simply sent over the green path. So that's nice, but how does it work? How does it perform in practice? To do this, we did simulations on 3 different topologies from topology zoo and also on FAT3 topology, where we measure the join acceptance rate, which is basically simply the proportion of joins that have succeeded, which means that they have reached the router directly connected to the source. And we measured this acceptance rate according to the varying network load. So here we define the network load as the mean number of concurrent multicast trees that are present in the network. And we measure joins acceptance rate according to it. In practice, during the simulation, we use a random number of multicast entries in the range 55,000 to represent the spread that we have seen on the real routers. So what we can see is that at low loads, we don't have any difference in the joint acceptance rate, which is totally normal because the network has plenty remaining entries and then they are never saturated. But if we increase a bit the load, we can see that it becomes more interesting as our methods, both Brunt SP and as shortest widest path, allows to have roughly 22% higher joint acceptance rate compared to classical PIM, which directly translates to more concurrent it wants to go to the next slide, which directly translates to more concurrent multicast tree present in the network for the same routers. So we have the same network, but we can have more concurrent multicast trees. And if we look at the other end of the spectrum, we can see that high load, we don't see any difference again, simply because the network is saturated and we don't have any alternate path to route the joins on. So that's nice. We can have higher joint acceptance rate, but every gain comes with a trade-off. And basically, the solution trades the path length optimality for a higher acceptance rate. Because when we route the joint on alternate path, they may be longer to accommodate the multicast feed capacities limits. But overall, we can see that the overhead is roughly limited, because we are roughly between 1 and 3 additional hops for all the multicast joints. In practice, you also have some impact on the flooding, because you need to send this information through the network to inform the other routers of the capacities. And so you need to flood this information and keep it fresh. One interesting observation is that when we increase the network load, the flooding is more impacted, which is in fact directly represented by the fact that when you have more multicast flows, you use more alternate paths, and if these alternate paths are also overloaded, basically they need to send more information to say that the multicast entries have been exhausted. And finally, you can also see that depending on the actual topology, the number of advertisement changes, simply because the number of alternate paths that are existing in these topologies may differ. Okay. So in conclusion, in our work, we have shown that PIM does not consider the multicast FIB capacity currently, which can directly lead to multicast tree creation failures, which are quite annoying for clients. In our paper, we have proposed to expose these capacities with existing linked protocols, such as OSPF and ISS, and then use this information to route the joins around exhausted routers. Using this approach, we can increase by roughly 22% the joint acceptance rate, which directly translates to more concurrent multicast trees for a similar network. As future work, we are also considering how we could use other metrics, such as bandwidth and delays, in the joint creation, in the tree creation process, such that we could have bandwidth optimized or delay optimized trees. So thank you for your attention. If you have any questions, feel free to ask them.
Thank you very much. So let's start with questions from Max.
Hi, Max Franke, TU Berlin. Very nice work. One question about, considering that multicast, often you know the capacities of the flows, right? And they're predetermined and fixed. So for a video stream, it would be a certain bit rate. Have you also considered including the available link capacity in your idea to make sure that the links between the routers also support the capacity that the multicast stream would require?
If I understood correctly the question, so you ask if you could include link bandwidth in the tree creation process. That's it.
Basically, yes. So you can at the same time make sure that you route the multicast in a way that the link is supported.
Yeah, you could do. We don't do it in the paper, but basically you assume that you have links to protocol, so you can do whatever you want on the join, on the path computation for the join. So if you want to have a multicast tree that you know will use like 16 megabit per second, you can say, okay, I want to exclude all the links that have only 8 megabit per second capacity. So you can reroute the joins on these paths.
Okay, that might be a worthwhile extension. Thanks.
Thank you for your question.
Thomas?
Some protocol engineering questions or remarks. I mean, PIM is called Protocol Independent Multicast, and that means it's independent of the unicast routing protocol. So I wonder, could this be engineered in PIM itself, not in using OSPF or ISIS? That would be the first question. The second question would be a bit, I mean, the whole signaling gets only interesting once you're approaching overload. And typically the signaling will also lead to rerouting that is sort of local, typically. So the question is, wouldn't it be more appropriate to only signal, instead of flooding all the time, the stuff, only signal overload or close to overload thresholds to a local region so that you can circumvent the problem of overload you address?
Thank you for your questions. So basically, indeed, PIM was protocol independent, but if you want to have this information, capacity information, you would need to have information about the old topology. And what we did was assume that we have a link state protocol because it has basically become the norm. And we inspired ourselves from segment routing, which also tried to do MPLS by assuming a link state protocol. So we took a similar approach than segment routing. And for the second question, which was about
local threshold.
Yeah. This was in the backup slide, but it's not problem. So basically, the thresholds are not balanced. So we try to put coarser bands at low utilization. So basically, you have a threshold at 50% utilization, then at 75, then 87, which makes that the threshold bands are narrower at high utilization. So that if you have plenty available entries, you don't flood the network always. So we would try to take this fact into consideration during the proposition.
Okay, thank you very much again. And our next speaker is Fariba. She is with the Max Planck Institute in Saarbrücken, and she will talk about how to detect IPv4 subnets in the wild and why it is important.
Yeah, just like next, yeah, that's good.
Good afternoon, everyone. Today I'm. Okay, sorry. Good afternoon, everyone. Today I'm going to talk about our work detecting IPv4 subnet in the wild. And this is joint work with Max Planck, TU Berlin, and TU Delft. So why is measuring subnet is important? BGP announces prefixes, and this is the aggregated view of the information. However, network operators inside of their network, they partition their prefixes into subnet, a smaller network, and these subnets, usually a structure of the subnet that they are using internally is not visible for us. And this is exactly what we want to identify or discover in this work. This maybe help us to better understand that help us understand that IP resource utilization or the network operation task, and also will give us more accurate abuse handling, blacklisting, and geolocation, which is published in the RFC, recently published in the RFC 1997. Before going in the detail, I'm gonna give some overview of our methodology. We used two complementary methodology, which is one of them is the ICMP echo, and another is the ICMP address mask. We all know that each subnet has a network address, broadcast address, and subnet mask, which defines the boundary of the subnet. For echo methodology, we ping broadcast and network address, and based on the responses that we get, we identify we somehow tell that we infer the structure of the subnets. And I'm gonna first focus on the ICMP echo, and then later I will explain the address mask as well. How does it work? We have in this simple example, host and the router over there, and we want to ping the router. In the normal situations and the norm that we expect, the router replies with switching the source and address destination like the simple reverse. This is what is exactly explained in the RFC 792. Just switching the destination address and the source address in the just quoted here as well. Now, unfortunately or fortunately for us, it's not always the case. Sometimes we ping the broadcast address like this, and the answer that we get is different from that supposed to be. So this is the help us to do our measurement here. There are some legitimate reason for using that's different address for the reply, which is like there's a maybe in the different configuration, a specific configuration in the routers or the load balancer or loopback address answer the request. But what we are interested in this work is to see how different routers handling broadcast and network address ping. To do so, we have a very simple setup, like simple experiment lab in our inside network, which is controlled environment, and we test a few hardware available that we have in the experiment. This is the schematic of the one that we did it in our lab experiment. We want to probe the network over here, and every time we check the other, we replace the router in the middle with different hardwares. By sending the echo request, for example, in the Juniper case, by sending the echo request for network or broadcast address, Juniper simply, by response with the address that ping sent. For the MikroTik, it simply drop the request, and for Cisco, more interestingly, it behaves differently, and it puts the receiving interface in the response back to the host. And we know that we cannot generalize that because we just test a few hardware in the lab experience, so different OS version, they might behave differently. But it can allow us to reveal subnet boundary in the web. So we did this experiment, and we use this method in a while. We crafted ICMP messages and put the destination IP in the payload, and we did our measurement, and all routable IPv4 addresses on November 2025. Then, if the expected behavior is like the putting in the response that the payload and the source address would be same. If there's a mismatch, we mark them and filter them out for the subnet detection. Based on this method, we identified 5 million point two addresses, which we detected 2 million subnets. But to see how different vantage points have effects on the R measurement, because every packet in the internet traverse different route and they have a different path discovery. We have 4 vantage points, one in the US, 2 in Germany, and 1 in Australia. And to see that our detected subnets, how they look like, in this offset plot shows that overlap of the different vantage point, detected subnet in the different vantage point, and the bottom you see that the different combination of those vantage point. And the bar shows that how many subnet that we take in each combination. 55% of the detected subnets we discovered from the old vantage point. 14 of them, they are only visible in the one vantage point, and 31% is discovered by 2 or 3. So we can say that having more vantage point can greatly affect the ICMP encode method. We just checked with the 4, but we left that how many advantage we need as a future work. There's another element in the cool element in the ICMP, which is ICMP address mask. Simply, a host wants to learn about the next mask, put the 0 in the mask, and the gateway answer that with the subnet mask in the reply. This is deprecated ICMP message, which was introduced in, with RFC 950. It is deprecated, but it doesn't mean that it's not supported actively, but it doesn't mean that they aren't used deployed in the internet. So we are using that to find the subnets as well. By this method, we find 2.3 million addresses, which gives us the 1.8 million subnets. And these two method contribution is over here in this plot, and overall we find less than minimal 25K overlap on both methods, because ICMP address mask by default disabled in Cisco devices, but there are other vendors that are using this. They are still using address mask, and they are enabled in their devices. And yeah, as you can see that in the plot, SF30 and 31, they are most common in our data set. But we also interested to see the pattern of the vendor that we see in the data as well. We did the SNMP version 2 fingerprinting technique, which is introduced by Taha et al. In IMC 21. And among those addresses that we find as a mismatch in the echo method, 44% of them, they respond to ICMP version 3. And as you can see in this plot, 98% of them, they were Cisco devices. And there are 2% margin of the error, we say, because we cannot confirm their behavior. In the second method, we only found 25% of those, the vendor of the 27% of those addresses. And they are, this is a top 5 vendor that we can see here, which is responsible for the 90% of these 27 responsive addresses. So based on the ICMP echo method, which is based on that we find in our measurement, is only applicable in the Cisco devices, and also based on the lab experiment that we did, it's indirectly validate our finding. But in contrast, several vendors allow ICMP address mask replies by default, and they allow that over the internet. To summarize, based on these two methods that we proposed, we find 3.8 million of the subnet mask. And we want to look at later on to see what we can find more in the address set as a future. Thank you.
Thank you very much. Yes.
Yeah, I do have a question. So the directed broadcasts in ICMP have been disabled in a lot of Cisco devices for the directed broadcasts.
I can hear you properly.
Can you hear me in the room, or is
yes, very well.
Okay. If you can repeat what I said, right? Like the directed broadcasts have been disabled in Cisco routers for like a very long time. So what is the configuration you tested with?
Direct broadcast is the configuration for the address mask in the Cisco devices, and by default, because of some abuse amplification that they have, it's by default disabled. By default disabled.
Correct. So you enabled it to test it. Is that
for the Cisco devices? No.
Okay.
Because we just measured over.
But maybe then the question is, which firmware version did you consider? How old was the firmware version?
Yeah, we have a few devices for Cisco. We have 2,900 series, And for Juniper, we have MX 150,
Mhm.
and MikroTik is the instance of the host.
Okay, thank you.
Any further?
Hi, interesting study. I'm Sam from University of Toronto. Sorry if I misunderstood something. For example, in your finding, you saw dominance of /31, but that subnet doesn't have broadcast address, and I think your method relies on broadcast address. How is that possible? And another question is, did you validate your finding with network operators?
Did you,
Oh, you didn't hear?
Verify with network operators.
No, we just tested ourselves in the lab experiment.
And about the first questions, since your method relies on broadcast address and /31 doesn't have a broadcast address, how did you detect that?
We did some filtering. A study is already gone. We did some filtering. If the address broadcast and the network address, they respond by the same address. And in the middle, because there might be other servers in that they respond that, we keep those only that mismatches. Other than that, we dropped it. It's not there anymore. I can show it later in my result.
Maybe I'll read the paper. Thanks.
No problem.
then thank you very much. Who's the next speaker, who is Kilian. He's a PhD student in Georg Kades group at TU Munich, and he will talk about reliable VPNs with Mask.
Yes. Hello, my name is Kilian. Recently, we did some investigation on reliability improvements of virtual private networks, and I want to share some results of our investigations. Typically, VPNs are used for establishing end-to-end connectivity between devices and to encrypt the traffic along the way. However, there are some more demanding use cases that demand reliable properties of VPNs, for example, for legacy applications, for wide area networks, or also for site-to-site VPNs. And when we talk about reliable VPN properties, we mean loss recovery, so low loss, and minimum delay. There are some basically standard software around that are frequently used. One example is WireGuard, which is part of Linux. It uses UDP for transport, so it's unreliable and has a rather minimalistic feature set and only operates at layer 3. OpenVPN, in contrast to that, is a user space program, offers reliable transport over TCP and offers unreliable transport as well over UDP and can be configured over layer 2 and layer 3. With Mask, we have a new basically standardization effort which builds on top of HTTP. You typically implement it in user space. We can use HTTP capsules for reliable transport or HTTP 3 datagrams that then again map to quick datagrams for unreliable transport. And now we have basically standardization activities at layer 2, 3, and 4. So what mechanisms do we have available for building reliable VPNs? Retransmissions are basically well known. They are part of TCP and used in quick streams. We need to be careful there. TCP meltdown is a problem that occurs when we nest different congestion controlled protocols that use retransmissions within each other. The congestion controller gets confused by increasing delay that is basically coming from the retransmission. So the throughput can sink. So yeah, so we need to be careful about this problem. Another opportunity that we have is to use forward error correction. Recently, there was a lot of research activity there that discussed different extension of or experimental extensions of QUIC. So there's not a standardized extension yet, but many things are moving there. And also FortiGate has a VPN appliance which uses some block coding scheme. We can get some independence of problems on an individual path by adding additional paths using multipath connections. There are experiments with WireGuard and OpenVPN in this regard, but also now we also almost have the multipath quick standard, so we can use that to build a multipath mask connection. And we can go even further by then building a network overlay by nesting different mask sessions within each other. It's depicted in the figure on the bottom here. We have a client and a server in the autonomous system A and D, left and right, and then we basically use an VPN relay in autonomous system E as a jump host, and with that we can, for example, circumvent peering issues by basically performing some sort of source routing or generating synthetic path with it. To perform our investigations, we built a special measurement setup. We're using NetAmp for the path property emulation in a symmetric configuration. And client and server side, we use the different VPN software, which is WireGuard, OpenVPN, and Mask in different configurations. For Mask, we built our own prototype, which is based on the multipath Cloudflare quiche fork by Quentin de Koning. And then we extended it with Tetris forward error correction scheme and connection nesting. For the scenarios, we use different properties. For example, the normal property only uses symmetric 20 milliseconds of delay. And then we have scenarios, for example, for random loss and burst loss, where we use a Gilbert-Elliott loss model. The measurement traffic is generated by IPERF3 in UDP mode. We use the really slow measurement rate of 1 megabit. So why are we using such a low measurement rate? Initially, we measured the throughput without any impairments, and there we achieved with WireGuard and OpenVPN a throughput of around 1.6 gigabit per second. Also, it's noteworthy to see that there is a bit different behavior of WireGuard and OpenVPN. With WireGuard, apparently we weren't able to basically put more traffic inside the WireGuard socket. With OpenVPN, we could put more into the TAN socket, so it's behaving a bit differently there, but still the throughput was 1.6 gigabit per second. With Mask, we achieved 600 megabit per second. We didn't do any further optimizations, but for our measurements, it was fine. We are living with this rate. And also, there are other reports of using Cloudflare quiche with much higher rates. So I think there's opportunity for improvement. And then we switched on random and burst loss and repeated those measurements. And with mask over datagrams, so the unreliable mask case, we already encountered issues at a slow rate of 1 megabit per second. And then we did some manual investigations and figured out that congestion control actually is blocking us because it treats those lost packets as congestion signals and somehow misjudges basically the available bandwidth. So it's basically an advantage and a disadvantage having congestion control within the virtual private network. And then we went ahead and did the actual delay and loss measurements at this rate. Initially, we didn't configure any reliability. And already here, we see some differences between WireGuard, OpenVPN, and Mask in the basically UDP or datagram mode. We see a bit of additional overhead or a bit of additional delay for OpenVPN and Mask because they are user-space programs in contrast to WireGuard, which shows a bit less delay in this case. If we switch towards the random and burst loss measurements, we see that Mask shows some higher tail latency here. We can again attribute this to the issues with the congestion control that we encountered also in the previous measurements. And we see also that the loss percentages in the table on the end-to-end path and the inner path are a bit different. This comes from handshake processes, handshake packets, and additional signaling packets being exchanged. Next, we switch to a reliable transmission. We see that on the end-to-end path, there are no losses. And we also notice that OpenVPN somehow introduces some additional delay in comparison to Mask. We didn't investigate this further, but it's still an interesting find. And as soon as we switch on the random and burst loss, of course, we get a high tail latency, which is needed for the retransmissions of around 100 milliseconds. On the end-to-end loss, we don't have any, on the end-to-end path, we don't have any losses. However, on the inner path, of course, we have losses that are corrected by the retransmissions. If we use forward error correction, we are basically down to only having our mask implementation available. There the end-to-end latency shrinks, or one-way delay shrinks to 44 milliseconds. Of course, this depends on the proper tuning of the forward error correction, sending enough repair symbols to be able to reconstruct it. So it requires some kind of previous knowledge on the link characteristics. But in this case, so this was our result, what we could measure. And also there is no end-to-end loss visible here. Then we extended the setup, adding a second link between client and server, and performed the multipath measurements. We kept one path with the normal configuration, so the 20 milliseconds of symmetric delay, and iterated for the second path through all other impairments that we showed in the table previously. We found out that on this bottleneck and high delay scenario, there was an increased tail latency. For one, it takes some time for the quick implementation to gather the path metrics, and before it switches to the other path. Also, the multipath scheduler somehow becomes a critical element of our VPN system now. So we need to be careful which scheduler we choose. In this case, we use the low RTT scheduler, which basically selects the path with the lowest RTT, so it doesn't react, for example, to losses. So we also have some loss on the end-to-end links here. And then finally, we extend the setup further and add basically this nested connections with a network overlay, generating basically artificial paths in between. And in this case, the scheduler basically chooses the perfect path, and we get, with our configuration here, a much lower delay, giving us the opportunity basically to improve the end-to-end link quality. So in conclusion, in Mask, the congestion control is always on in comparison to all other VPN systems. So we can, if we are not careful, can perceive blocked forwarding on lossy paths. Our prototype currently achieves less throughput at OpenVPN and WireGuard. We evaluated Mask with retransmissions, forward error correction, multipath, and overlay. With the exception of forward error correction, all of those mechanisms are standardized, or nearly standardized, let's say. And we found out that forward error correction and retransmissions both avoid end-to-end losses, with the advantage of forward error correction that we have the opportunity to reduce the delay that is needed for loss recovery. And with multipath and overlay, we have interesting tools available to circumvent issues of low quality paths. And we have some more results in our paper with high delay measurements, bottleneck measurements. And that's it. Thanks for listening, and please ask any questions.
Thank you very much. Any questions? Audience? Then maybe a brief question, clarification regarding the implementation. Is it available for which platforms? Is it Linux, Windows? No problem.
It's a Cloudflare quiche library. It runs surely on Linux. I think it also runs on. I think it should run on any platform, since it's basically used as Cloudflare's VPN gateway, which can be installed by anybody. So okay. I think it's quite independent.
And how much, I mean, do you think, do your results depend on the actual quick library? I mean, is there any side effects that might occur?
So this forward error correction library is kind of independent. Of course, you need to hook it into the proper parts in the quick library. I mean, you need multipath support, which is now coming into towards more quick libraries. For the connection nesting, I think this can be done basically as part of the application. So yeah, most of it is available. Sure. And it would be interesting to also have the forward error correction standardized somewhat to make it usable for more people.
Yeah. Okay, cool input with IETF. One more question?
Yes. So yeah, my apologies if you covered this already at some point, but
please state your name.
Yeah, what are some use cases where?
Your name.
I'm Diwan from Chinese U of Hong Kong, yeah, apologies for if you covered this already, but what are some use cases where we want VPN to be reliable? Right, like yeah.
Yeah, so there are like really old applications that are not intended to be operated over wide area networks, but somehow they need to be operated over wide area networks. So this is one use case. But I think also in general, site-to-site VPNs, you can benefit from such improvements. I think to have like more robust connectivity between them.
Okay, thanks. Further question? Nope. Then thanks again. So where's our next speaker?
Beijing, if you're removed, like ask me for slide sharing permission and I'll grant it.
Okay. So Beijing, he's with University of Maryland, and he will talk about RTC relay server infrastructure study. Join us remotely. Or not? Do you hear us, Beijing? Hello.
Hello.
Yes, we hear you.
Yes, cool. Can you see my screen share?
Nope.
Okay,
This is empty.
So how about I share the slides and I give you control?
Oh yeah, that should be pretty cool. Okay, cool.
You have control.
I see. Okay. Yeah, good afternoon, everyone. Yeah, thank you, Suresh, for letting me to host remotely. So this is Beijing from University of Maryland, and today I'm going to introduce our paper RTC Relay Server Infrastructure Study, which is a joint research project done with Meta. So, okay, I see. The animations is not here, but we're easy to go with. So basically, today we have popular RTC applications. For example, like it covers our daily life, like chatting with friends, conferencing, interviewing, video sharing, etc. These apps like Discord, Messenger, WhatsApp, FaceTime, Google Meet, Zoom, etc. They cover like they sync it into everyone's daily life. So basically, from user or researcher's perspective, we always see the client end. So basically, the apps they deploy on our client phones or iPads or our laptops. But which in between is the RTC infrastructure. It remains opaque and it is like always hidden from the companies to the users. So in this paper, we're going to look into what's happening between the client when we make the call. So an interesting question is to look into is by looking into the media pass. So basically, let's say media pass, we see how it is established. For example, we have two RTC clients. Though the animation is not here, so the picture will look a little bit messy, but we can still see that it will first try to look into whether the two clients are publicly reachable. So if it is, then a P2P connection is preferred to be established to transmit the media packets. And if the two clients, their public IP addresses is not reachable from each other, and a fallback session through the relay server, or we say the turn server, is established. So it means that it's serving as a proxy or a bridge that every media packet goes through this relay server and back and forth between these two client devices. So in this paper, we have the background to see, okay, what relay or turn server is. And the next question we intuitively ask is, if you are running an RTC service or RTC company, and you have a budget of, let's say, 10,000 servers in hand, how are you going to deploy them? Or we say, how are you going to build the relay server infra? So generally speaking, there are two methods of doing so. So one is more centralized, which means that you can potentially have like longer core latency because it is potentially not that easy to get a relay nearby hand. And the good thing is, for example, it is easy for load balancing and it is easy to maintain because there are fewer nodes physically. And the other way is we do it a more scattered solution. So for example, let's say we can distribute them like across 10 or 20 cities across the country or the globe. So this will give you potentially lower core latency because it will be easier to get a relay server like nearby hand, but the cons are there could be like higher maintenance challenges because you have more physical nodes to maintain. So these things, they're all like theoretical to happen. So let's see what the companies are doing. So in order to build such study, we study three core problems. So the first thing is the relay map. So we're going to plot the maps to see where the servers are located. The second thing is when we get this map, it's easy to ask, okay, so we got a map. So which relay in this map or among all these cities or all the nodes is going to be allocated to serve this particular core? And the third thing is we have so many relay nodes in the world. So are there any plan Bs if the current relay goes offline in a core? So the fallback basically measures how robust the core is. And in this paper, for now, we cover three popular RTC apps, which are Discord, WhatsApp, and Zoom. And for Zoom, we cover both the free and business accounts to show the comparison. And we'll have more apps like to be covered in the future work, which will be an interesting angle to dig in. So basically, for the measurement challenges, excuse me, can we switch into like the animation way so that we don't have the covered?
So,
yeah.
I don't think we can change the slides.
He has control.
Yeah.
Do you want me to take back control? Because you have the control.
Yeah, I mean, the animation is gone, so there will be like slides covered with the
table. What do you mean?
Oh. Never mind.
No, but we cannot change this. So that's a static PDF. We cannot change the slides, and that the table is covering parts of the slide. I mean, I think should do it on the audio track.
Okay, let's just see like if we can just go on. So basically talking about the measurement challenges in order to proceed with such study. So for one thing is we need to make enough cores from all over the world. And the solution is because we cannot fly or like telepathy to anywhere in the world, right? So basically we use the cloud infrastructure. And the solution is we use our phone to be connected to certain Azure VMs distributed globally, which are listed in the map and the table here. And the second thing is we need to make a lot of cores. So basically we need to scale up the repeated number of cores. And the solution here we use is we use the Xcode app installed on the laptop to automate the tapping of the picking up and hanging up buttons on the phone's mobile front end. So basically the measurement testbed looks like this. We have MacBooks, we have Xcode installed to control the caller and the calling phone. And both the phones, they have WireGuard VPNs connected to the Azure VM. And on Azure VM, we have Wireshark installed so that the packet traces can be collected. Using these RTC traces of the PCAP files collected, we analyze it and we study like where all the packets they are sending towards, and we diagnose like what the relay server IP is. So after we get this relay server IP, we need to identify the locations. So we have three steps here. So for one thing is we study the IP intelligence services, for example, like IPinfo.io, to see what it tells us about the relay server location. And after that, we need to further verify that it is true. So we carry out 2 steps. One is we verify the geolocations by latency triangulations using the VMs we have in hand. The third step is we trace road to the IP to verify any city information alongside. For example, IAD means the Dulles Airport near DC. So this information can also help us provide further confidence of the measurement result. Okay, so there could be some display issue here. Like, for one thing is we show the Zoom free account relay map. So in our study, we find out that Zoom provisions 2 tiers of relay infrastructure, and the business account we show here has substantially more relay nodes than the free account. So we observed only 2 relay locations of Zoom free account, which is located in the US East and West Coast. And both of them are run by Zoom itself. Okay, it seems that there's like some display issue here. May I request you like share my screen again? Like the
Can you reshare the screen?
Yeah.
Can you try again? Wait.
So basically speaking, like for the Zoom relay map, we only have 2 nodes observed globally. And for the business accounts, we have substantially more nodes observed globally. We have 11, like from our measurement scope. And note that like all of them, they are run by Zoom itself. For Discord, the thing to highlight is it uses a hybrid relay infra. For example, 80% are run on Cloudflare, 16% on Google Cloud, and 5% nodes are run on i3d.net. Observe only Tokyo. For WhatsApp, it exhibits the broadest relay footprint among all the studied applications, which have 25 relay locations globally, and all of them are owned by Meta platforms. So from the targeting point of view, Zoom and Discord, we see that they run under a fixed caller region, and there are repeated calls selecting the same IPs or the IP prefixes of repeated calls. And Zoom, unlike Zoom and Discord, WhatsApp, on the other hand, adopts a joint caller-calling aware targeting. So it allocates 3 relay candidate IPs through 3 stern binding requests at the start of the call. And 1 relay is picked based on the end-to-end latency measurement through the stern binding request and response. So when talking about the fallback, we see that for Zoom and basically we count the number of sessions, the UDP sessions and TCP sessions to see how robust the call is. So counting them together, Zoom free account has 1 UDP session and 1 TCP session. Discord has only 1 UDP session, which makes them both non-robust. And for Zoom Business, it has 1 UDP session, and if you block that, there will be multiple TCP sessions, including 1 on the original Zoom relay and multiple on AWS fallbacks. And WhatsApp has 3+3, which makes them more robust than the other 2. So after studying the locations and the targeting of the strategy of these relay applications, we then see the latency measurement, which is a result of the previous. So we see that on first thing is a denser relay deployment always brings down the core latency. For example, in these figures shown here, the darker or the deeper color of these boxes shows a higher latency. And we see that for Zoom free, the general color is the most deep. And for WhatsApp, it's light. So it just gives us a general latency comparison, which is Zoom Free provides higher latency than Zoom Business in Discord and higher than WhatsApp. And also we show that geographically close calls are primarily more benefited through like more relay nodes deployment. So if we see on the diagonal of these figures, we can see that, for example, like Zoom Free has only 2 nodes globally. The diagonal is most deepened. And for WhatsApp, it is most light. So basically, it seems that it's not always beneficial, for example, if you are going to have a shorter latency to subscribe into a higher level of account. If you are both, for example, living near the relay, the caller and quality, it is substantially not necessary to purchase such higher services. So running in conclusion, in this paper, we see that denser relay deployment and smarter targeting both reduce the core end-to-end latency. And the hosting models, they can differ from the company to company. And the fallback robustness varies. And interestingly, these results can change. So our study is measured through August 2025 to March 2026. The reported numbers may shift as the providers reconfigure through time and space. And there's a lot of future work that can be done like after this. The first thing is we need to make repeated calls over time and space. The second thing is we can try to extend the measurement nodes to a broader scope. And then studying different devices can also be beneficial. The last but not least thing is we're welcome to follow up work on more platforms. Okay, thank you. So happy to take any questions if there are any.
Thank you very much. Danish, go ahead.
Danish from MPI. I have just one question regarding the using Azure as your vantage points. How that can skew your results at the end?
So basically, we say that there is 100% the chance that there are relays that we are missing, like in this part, because we're using Azure, only 13 nodes of them. So in our paper, we just bring, for example, to some level of like comparison between the companies. For example, let's say for Zoom free account, we only observe 2, and for Zoom Business, we observe more. So in this matter of fact that we cannot guarantee that we observed every single relay and every single IP in the world, but we just say that using the cloud infrastructure, it gives us the ability or versatility to make phone calls across the globe and detect the relays distributed globally. So I wonder if this answers your question.
Yes.
Thank you.
Thank you very much. Any further questions? If not, then let's thank the speaker once again.
Thank you.
And now, last but not least, a short paper by Innocent. He is with the University of Washington and will talk about towards extensible, auditable, and modular measurement specification and execution in computer networking.
Great.
And we wait until the slide deck is shared.
Can everyone hear me?
Yes, perfect.
Is it possible for me to screen share?
Yeah, so the share is currently enabling the sharing. Waiting. Now we see the slide. Now we see your screen actually. Perfect, and the slide deck.
Okay, great. All right, everyone. My name is Nissen Obi. I'm a PhD candidate at the University of Washington, presenting a paper done with my collaborator, Sia, who was an undergrad researcher with me. Experiment and measurement are two overloaded words in computer networking. And so this is something of sort of our attempt in building an experimentation platform to add some logic and reasoning to this work. So first we'll talk about the semantics of measurement. In an active measurement, say we have access to a ping resource through some programming interface, the black box you see on the slide, by constructing probes. We can think of the white boxes north of the interface as the client side, and the white boxes south as the service side, the north and the southbound interfaces. We can present this capability as a relation. And so the interface, the ABI on the slide, is a subset of the Cartesian product of a probe and a ping. And so each ABI is uniquely defined by a probe and a ping resource. But there are many such things that we can use to ping. And so this is a little bit unstructured. So let's generalize this a little bit more. In this case, all the information that we were hiding previously in the ABI is a little clearer. We have another white box called Scamper that is south of the probe and north of the ping resource. And now there are two new interfaces. The ABI is now an expressing a relation between probe and Scamper, while the HAL is expressing a relation between Scamper and ping. Now, the distinction between the client side and the server side is a little clearer. One thing to note in this formalization is that we can express the relationship by the Cartesian product of the white boxes, or by the product of the relations, the black boxes, these interfaces. And the key idea is that the relational point of view is a more powerful abstraction. And you'll see kind of where we're going with this. So say you don't want to use Scamper, but you want to use something else that supports pings. And so we want to be parametric over the implementation of the resource like ping. This motivates the addition of a resource white box and new north and southbound interfaces around that. And so this generalization and abstraction allows us to discriminate and decompose context. But as we're doing that, we're adding fixed points in terms of our abstraction. And so as we generalize and we create these white boxes and interfaces, the interfaces act as guards for our white boxes, guarding the north and the southbound interfaces, playing the role that a protection ring would play in, let's say, an operating system. And so, for example, if we wanted to switch out, let's say, Scamper for the default Linux ping utility, it would be as simple as just exchanging that component. And we can see that the impact of this change is local. It can be done without breaking policies defined at higher levels, but commuting with those defined at lower levels. And so the interfaces become places of defining behaviors between these white boxes. So MTL, which is the work that we do and we present in the short paper, is sort of a universal adapter. And so we'll walk through this kind of diagrammatic calculus, kind of demonstrating what it would mean to specialize in MTL ping resource. And so our base MTL template is free, so it has open incoming wires for probes and outgoing wires for resources, meaning that it captures the entire universe of probes and resources. We specialize this by defining a resource interface called our ABI. You can think of this as ping. And now, like in algebra, we can join and compose these two together and match and identify the resource wires with the ping interface wires. And so the result is an MTL module template that is specialized for a ping resource. We have reduced the universe of possible resources to those that implement ping. On the other hand, we have the same ping interface, but now we have Scamper running on our Linux machine, for example. And so Scamper has its own API that allows it to be interacted with. And to make this MTL ready, we compose Scamper with our ping interface. So the result is an interface constrained Scamper. Now, since our previous resource specialization has a southbound that is a ping interface, and our now constrained Scamper has a northbound that is a ping interface, by definition, we can combine these on a common north-south interface. The result is a Scamper resource module which fully implements ping and can receive ping valued probes. That is, a specialization of the southbound works inversely to restrict the universe of possible probes that can be executed on this resource. And so in our short paper, we kind of motivate.
So, sorry, Innocent, you're way out of time now.
Apologies, I thought I had 4 minutes.
You are eating into your question time. If you want to go ahead and summarize, like you can go ahead and close. Yeah.
So the way we do this in the paper is we motivate an essential, like typing, and two semantics for the context. This looks something like this. Basically, we can turn our language semantics into these diagrammatic calculi we use. Our motivation is to think of ping as operations versus the usual way of thinking of ping as utility. And so our overall view is that there's a deep algebra underlying this, that thinking of ping as operations motivates thinking of these algebraic signatures, and ping as utility as these algebras that implement our signatures. And so we can think of our measurements and our measurement experiments, or measurement scripts as these implementations. So I'll stop there, yeah, we'll open for questions.
Thank you very much. So, any questions? Maybe then just a simple question. I mean, that sounds all very theoretically. Is there any concrete implementation? I mean, I see some code here. Is there an open source implementation that can be downloaded?
Yeah, so we don't have a public implementation yet, and so that's what kind of we're working towards in our paper. But we have a proven model that's worked in our lab environment, and so what we're doing now is working on releasing a Go library that has some of these semantics built in. But we have demonstrated kind of lifting a Scamper implementation and kind of running pings on Scamper using this framework.
Okay, cool. Looking forward to the extension. Then, if there are no further questions, let's conclude the longest session of this workshop. Thank you all. Enjoy the break and come back 4:30 to the session on transport and media.
Thank you, Matthias. Thank you very much. So, in other conferences, when you have remote participation,